Sir, you can start the lecture.
Okay. Okay, great. Even though it looks like everybody is not here, let me start the second bit. I'm sorry we had to change the time today. I had to go for a serious meeting this morning. And one of the things that I wanted to mention from yesterday's experience is that, of course, now the number of people on the on the small. Can you please everybody mute your microphones? Yes. But it is very difficult for somebody who's teaching a class like this to do this in a very cold manner. There is no feedback, no person speaking. I can't see your faces, so I don't know whether you're getting what I'm saying or not. And that is why I'd much rather do this in person here with 50 or 60 people in the audience, but I can see them. On the other hand, because of this new way of communicating with everybody, we can have a much wider reach and all over the country and with lots of people, keeping safe all over India. And the price we pay is that given that we have finite time, we cannot take questions as much as I would like to, as well as I don't see faces, so it really is not an interactive lecture. Normally, that's how, I mean, those know how important it is to actually have an interactive lecture. So let's see how we can strike a balance between the two. Yesterday, the number of questions was overwhelming, a large number of questions. So I would request you, like I did yesterday, to keep the questions to the point. At the end of the lecture, I'll have some time, but please to what I've discussed today and not everything, right? All of astrophysics, because I know there are lots of questions, and we can have such sessions where we can have questions from everybody and some of us can answer them. But this is only the beginning of the astrophysics course, and you will see that a lot of the questions that you had will be actually addressed in the course of the month, right? So that is a very important point. And the other thing is, of course, it's been set up. Dipanjan in the morning told you that there is some way we are setting up so that people can ask questions and we can interact with them offline. And let's do that. Okay, right. So I'm going to share my screen and continue what we were doing yesterday. Right. And okay, I hope I can be seen and heard. You can see my screen. Santosh, are you there?
Yes, sir. We can see your screen.
The screen can be seen? Okay, good. Fine. Right, thanks. So this is lecture 2. And if you remember, what we were saying is that we were talking about naked eye astronomy. And I'm going to do a little bit more of what we were doing in terms, and then I'll go and talk about the rest of the universe. So I already said that there are the star patterns in the sky. A lot of people talk in terms of constellations. To somebody like me who's an astrophysicist, these names and shapes are more of a marker, and it doesn't carry much significance, really, because these stars don't make up a Big Bear, Ursa Major. These stars don't make up a dragon, Draco, etc. But these are names for patterns, and it's like in Pune, I know where Sadashiv Pet is, I know where Shaniwar Bada is, and I know exactly where to go. These are markers in the sky. But the interesting thing is, a lot of people think that because the sky was in pre-television times, think about what entertainment there is in the evenings for you. There's no electricity, and so there are no phones to look at. And for most of humanity's history, sky is where the stories happen. It's available to everybody. It's free. And a lot of people had looked at the sky much more than they do now because we now stare at the television. But and a lot of things happened in the sky that people knew. People knew the sky. People knew the stars. People knew all of these configurations, so they knew, and they started making stories out of them. And a lot of stories got turned into folk tales and got incorporated into our history of folklore. A lot of people think that some of these it's not that the constellations are named after folklore, but folklore came from the constellations. A lot of the Ramayana and the Mahabharata, the stories that there are, actually incorporate a lot of the star tales that we have. And so there's a very rich interaction between the folklore of cultures and how they remembered stars. They had to remember the stars, otherwise they couldn't, remember the way to a village and back, things like that. They had to remember that there is this constellation next to that constellation. That constellation, they made up stories for. Now, I also told you that the ecliptic, that's the path that the sun takes in the sky, was considered special by certain cultures, not the Chinese, because the Chinese thought the entire sky is special. Chinese in history thought that anything that's happening on the earth, like an earthquake or a storm or a change of government, everything will be seen in the sky. So they actually wrote down minute detail, hour by hour, what's happening in the sky. And that is why now, looking back, all the records we have about transient objects, about stars exploding, everything comes from the Chinese because they made these records. In the Indian culture, as well as the Middle East, as well as Europe, we considered only this part of the sky to be special, the one that the sun went and the planets went by, because our astrology, even though I don't believe in astrology, but astrology is very important because that came into astronomy, is based on the constellations that go along this line. And you can see these are the familiar rashis that we have, the Leo, the Cancer, the Gemini, etc. So those are important. And I also told yesterday how, relative to the Earth, the sun moves, and that is very important to know. And it's actually the sun's orbit, and that is the ecliptic. The ecliptic is the sun's orbit. And if you look at it from the Earth's point of view, you get that thing in the sky. And then, but the interesting thing is, I also told you that in the night the stars move. As the Earth moves, the stars move in the sky, and as a result, depending on where you are on the world, then on the Earth you will see certain parts of the sky, but you won't see other parts of the sky. Now, you have to also understand that these stars are there during the daytime as well. Right? If you look at the sky now, you won't see a star, but they're there. But you can't see them because sunlight is scattered in the atmosphere, and that becomes brighter than the stars behind, and the air itself is glowing. And if you go outside the atmosphere, you will see the stars. Right? In fact, the sky is not blue if you go outside the atmosphere. The first time I ever met an astronaut, I asked them, I remember the first question I ever asked them was, what was the most striking thing that you felt when you went into space? And he thought about it a little and said, the sky was black. The sky is black outside, right? Because the sky, there's no blue in the atmosphere. That's an atmospheric phenomenon. But the atmospheric phenomenon also keeps because our eyes cannot integrate for very long, you cannot see the stars. On the other hand, if you're a radio astronomer, you can take a radio telescope and observe all day, because this light that you see outside is not there in the radio wavelengths. It's not scattered in the atmosphere. And so a radio astronomer is a 24-hour astronomer. I've often done quite a lot of work with the GMRT during the day. Right? Here is a good example of what happens. This is a deep picture of the sky, and what you see in the night, you can see in the day. If you take a camera and integrate and put a filter that filters out the scattered sunlight a lot, then you can see the stars there. This is taken during the day, a long exposure, right? So actually, the stars are there, and they're doing the same thing. It's not they're stopping rotating because the Earth continues to rotate. Okay, so that's also a striking picture to remind you that whatever is out there, outside the atmosphere, is always there. It gives you the illusion during the day that the stars are not there. Also, you also have to remember what causes the seasons, because this we learn in geography, but most people forget. And most people forget, and that is why a lot of people really think that it is hotter in the summer than in the winter, because the Earth comes closer to the sun during its motion in the year, and that's absolutely not right. A lot of people think so, and if you go around and ask people, that's the answer they will give. There's a famous documentary in which done in the 1980s, where a bunch of Harvard science outreach people made the documentary. They went and asked graduates after the convocation at Harvard University and MIT. These are people who are attending the best universities in the world. Coming out of the convocation, they asked some questions, and one of the questions was, "What do you think? Why do you think it's hotter in the summer than in the winter?" And about 80% of the people, even the ones that just got a degree in physics or mathematics or science, said it's because the Earth comes closer to the sun in the summer. And that's not true, because often you see these very elliptical orbits. The sun's orbit, the Earth's orbit around the sun is not elliptical. It is elliptical, but it's mostly a circle. The ellipticity is very small, less than 1% or so. So it is because, as you see here, the Earth is inclined. The Earth's axis, rotational axis, which I talked about yesterday, is inclined to the orbital plane. And as a result, in the summer, say this is the summer solstice, the day in which it is the longest day of the year, you remember the sun rises farthest from the east. And as you can see, the sun's rays fall on the Earth, but the Earth is at an angle. So in the northern hemisphere, they fall very directly, and in the southern hemisphere, they fall at an angle, like that. And if the sun's rays fall at an angle, then it is spread over a much larger area, and as a result, the amount of energy per unit area is much more. This is why it's colder, right? Whereas the more directly something falls, the more it can heat up. And also, I told you in the summer, the days are longer, and so you get the sun for a longer period, and that's why. So this is a very interesting thing about this. The tilt of the Earth does this. Now, I just wanted to debunk the other method. See, the Earth's, here is today, this year, the perihelion, which is the nearest the Earth came to the sun, was on the 2nd of January this year. And you can see the distance between the sun and the Earth was 147 million kilometers. The farthest it will be on the 5th of July, and that is 152 million kilometers, not much difference. And the remarkable thing is, 2nd of January, the Earth was closest to the sun, and that's in the middle of our winter, right? So it cannot be true that summer actually means that the sun is closer, the Earth is close to the sun. So that's one of the things that I wanted to point out in this story about the Earth and the sun that we are talking about. So the timing is the timing of coincidence. Why is this? And actually, this has also been changing, because I said the Earth's inclination is rotating as well. For example, here I've written that in 1246, for example, the winter solstice was on the same day as when the Earth reached its perihelion. So now it's 2nd of January, but it was on the 21st of December. And then every 58 years, it has been moving a day. So, for example, in AD 6400, the perihelion, the Earth's closest approach to the sun, will be on the 21st of March, the vernal equinox. So it's not a coincidence. It's just that we happen to be here at a time when this Earth's coming closest to the sun has become very close to the winter solstice. But this moves because the Earth's orbit is precessing. Not only is the Earth's rotation like that is precessing, but the ellipse around the sun, that also is moving slowly, and that is because of the attraction of the other planets in the solar system. Okay, so I quickly wanted to highlight something that I mentioned yesterday in response to a question, and that is the fact that I said that because we are in a plane, the solar system is a plane, then you see from the Earth the sun against these ecliptic, the 12 signs of the zodiac around the ecliptic, and so this is why we can identify a sign of the zodiac with a month, and this has moved around quite a bit. So first point of Aries was the question yesterday. First point of Aries was supposed to be on the 21st of March. The sun was supposed to be on it, and you can see it's moved quite a bit now. And so on the 1st of March and 21st of March will be here. Sun you will see in the middle of Aquarius. That's where you see on midday, and about 2,500 years ago, the sun. This thing was such that was Aries, okay? And this is why this whole system of astrology we have now, if you believe in it, is actually you can see how, even if you believe in astrology, the fact that when you are born is kind of predetermines your destiny. That system is completely wrong, and so that's complete fiction, right? So let me move on to the next phase. But I saw some questions. There was somebody called Shukonna who had a question. Can you unmute and ask your question, or has your question been answered? If you can put your hand up if anybody has a question on just the first part of what I said. Junik, I unmuted you. Go ahead and ask your question.
Hello, sir. Am I audible?
Yes.
Okay, thank you, sir. Sir, my question is regarding the orbital part of the planets that I just explained. Once I was reading the paper, the orbital eccentricity of Pluto is absolutely different from that of the other planets. Like as that for Earth, it is 0.017, but for Pluto, it's 0.247. And also, the elliptical nature of the orbit is very, very different from the other planets.
Yeah,
So
it's one of the reasons why
which
is one of the reasons why Pluto was discounted as a planet, and that is one of the main reasons. And that is because it is very clear that Pluto was captured much later. It didn't form with the solar system. There are many things wrong with Pluto's orbit. One of them is that it is completely out of the plane. Every other orbit planet is in the same plane as the solar system, but Pluto is out of the plane, and it is also it was the outermost planet. And people realized that it is, and realized that the only way that can happen, because the entire solar system formed from the same cloud, and so the angular momentum is defined by the angular momentum of the initial cloud, right? So that angular momentum is a vector. You can't change angular momentum. Angular momentum is conserved, and so the direction of the angular momentum is perpendicular to this plane, right? And so you cannot really have a system in which one of these things goes completely out of the plane. Then that has to be balanced by somebody else also going out of the plane, and thus balancing the angular momentum. And that is why one of the reasons people were convinced that Pluto has entered the solar system much later. I'll go for only one more question, and that is Anushka. Anushka, go ahead. I can unmute you. Yes.
Good afternoon, sir. Am I audible?
Yes, you are. Go ahead.
Sir, just before the slide, there was a slide about the ecliptic, which is defined as the plane of the Earth's orbit around the Sun.
Yeah.
And sir, yesterday when you were explaining about the celestial sphere, you said that there was another orbit sort of a thing.
No. Here are the orbits, right?
And can you move to the next slide?
No. So okay, next slide. Yeah.
Yes, this one, this celestial sphere, wherever it is cutting this.
Yeah. So please don't confuse. I'm going back to this one because the celestial sphere is around you. You are standing here on the Earth somewhere, right? And you can stand anywhere on the Earth, right? And so the celestial sphere is just an imaginary sphere around you, such that you can take these planes and extrapolate out, and so that will appear as a circle, right? So the celestial sphere does not exist. You're not covered by a bubble. Now there are two planes here, and please pay attention. The one plane is, if you take the equator of the Earth and extend it, that becomes the equatorial plane. That's the celestial equator. And if that cuts this imaginary sphere around you, that is the equatorial plane. Okay, and that's that circle. What is the utility of that circle? It allows us to. This is a celestial equator. As you can see, it passes through. That's the celestial equator. That blue plane. It passes through the equator. It allows us to define a coordinate system in space, the area and declination, the latitude and longitude in space, right? Because it's connected to the Earth. Similarly, the sun is not going along that plane, of course. The sun is going along a different plane, and that's the plane of the solar system. And these two are inclined at an angle of 23.5 degrees, right? And so that's this goes around like that, okay? And so that's the sun's orbit, and that's the ecliptic. Okay, and this is why this is why these two are not, and they intersect only at two places, and those are the two equinoxes. Okay. Right now, I'm sorry I can't answer all the other questions because then I'll be stuck here. Let me move on, and I'll come back. I'll have some time at the end of the lecture, and then we can come back and ask some questions. Thank you very much. Okay, let me just move on. Okay. So what I was going to do next is to then go away from this geocentricity, etc., and looking at the sky, and go back to the issue of how large the universe is, and what does the universe look like, and where we are in the universe. Okay. And for the rest of today and in the next two lectures, I'm going to talk about how and it's not naked eye anymore. We can use any instruments as we can, and how we essentially measure the scale of the universe, how we measure distances, and what we know about the scale of the universe, and how large the universe is, how far away things are. Okay. And I'll take you through what the main challenges are, because this is a very hard thing to do. One of the hardest things in astronomy is to look at these stars and find out how far away they are. That is the most important thing in astronomy to some extent, because think of the following. You see the sun and the moon. They're exactly the same size on the sky. They are half a degree across, and they're circular. You see them on the sky. Now, if, for example, you took them and you say they are same size on the sky, then they must be exactly the same distance away. That is absolutely wrong, because one is about 1,000 times further away than the other. And that is why, actually the sun is much bigger than the moon. Okay, so just looking things up in the sky does not tell you how far away they are. And unless you know how far away they are, you don't know, the scale of where you are. So that is why astronomy is such a new subject. Because even 100 years ago, in 1921, think about 1921, it's been 6 years since Einstein's general relativity has been published. The electron and proton have been discovered. The neutron has not been discovered yet. Quantum mechanics is coming out as a new subject. We are beginning to understand what's inside the atom. And yet in 1921, we did not know the size of the universe. We did not know that we live in a galaxy. We did not know whether the whole universe was one galaxy and it's full of stars, or whether the universe has lots of galaxies which are full of stars themselves. This issue was debated in 1921 at the National Academy of Sciences, and I'll come back to that later on in the third lecture, in talking about where we are, what is the size of the universe. No idea, right? So this is a very new subject, and this is because it is very difficult to do. And I will try and take you through this whole story of how we know what we know about the scale of the universe. So to know that, we'll have to figure out what galaxies are. And even though you might know now, it is worth looking through the history of how we came to know that we live in a galaxy. because that is the crux of this whole story of how large the universe is. So if you look at the sky, take that and you look at the sky, you, as I said, with a small telescope or with the naked eye, the sky has lots of stars in them. If you just take a small part of this and you look at it through a large telescope or even the Hubble Space Telescope like this one, this is what you see. Now, what's the biggest difference between this and that? And that is, in this particular picture, you see only stars. Nothing else, right? And in this particular picture, there are only two stars. That one and that one. All the others are galaxies. So here you can see that in that particular box, I chose just a random particular box. You probably see naked eye, nothing there. And if you take a telescope big enough, you might see a couple of stars there. But if you take a big telescope and take a very deep image, you start seeing through the screen of stars and you start looking at galaxies. And galaxies themselves have 10 to the power 10, 10 to the power 11 stars in them. And so each of these specks of light are 10 to the power 10, 10 to the power 11 stars. Right? And here you're looking through stars in our own galaxy through a screen. And I'll see in a minute. But this is what fox people. What people traditionally, even when Galileo started looking through the telescope, and in the 17th and the 18th century, looking through a telescope became very, very normal. People started making larger and larger telescopes. Here's somebody who did the most in making large telescopes, William Herschel. William Herschel, and the story involves people who are very peculiar people. In astronomy is a peculiar science to some extent. Herschel was, as you know, a composer and an organist in a church in Bath. He was a German who was hired by Bath to run the church music. And I've got lots and lots of music written by William Herschel. He had a sister who lived with him, Caroline Herschel, who was a singer, who was a soprano. And William Herschel's hobby was building telescopes. And in his back garden in Bath in England, he built the largest telescopes of the world. Now, I can't imagine doing that as an amateur astronomer now. In my back garden, building the largest telescopes of the world. But this is what he was building. This was the 20-foot telescope and the 40-foot telescope. Here, the foot means the measure is the size of the telescope. Normally, we say it's a 3-inch telescope, and that is actually the diameter of the mirror. That's the diameter of the mirror. But he referred to the telescopes as the length, and this is in his back garden. He's building these things. Now, Herschel built larger and larger telescopes, and Caroline in her autobiography writes that, my brother has gone insane. The whole house is full of lots of metal and glass, and that's all he does, and he doesn't, do his work and stuff like that. Then he suddenly became famous. Why did he become famous? Because he discovered a planet called Uranus. And he discovered a planet, and as soon as he discovered a planet, you become the most famous person in the world. And the king gave him a lot of money, King George III, and he became famous as an astronomer. And then Caroline started looking through his brother's telescopes. And actually, late in the night, William Herschel used to fall asleep very early. And Caroline actually used the telescopes, and she discovered 8 comets that were not known till then. Herschel did not, William did not discover any. But one of the things he did was that he found that if you look through a telescope at something like this, you start seeing stars that are not point-like and twinkling, but larger and fuzzy. And it was he who called these things nebulae. He used the word nebula, which means, of course, nebulous, as you know, which means fuzzy, right? Later on, I put the picture of John Herschel, which is William's son, who later on picked up William's work and continued it in the Southern Hemisphere. But what William did was he made a whole list of non-point-like nebulous stars. And this list is something that we use even now. It's called the New General Catalogue, the NGC catalog. At the same time, in France, there was somebody called Charles Messier. Charles Messier, around the same time, so William Herschel, we are talking about 1780s, 1770s, that kind of time. Charles Messier, at the same time, in France, was doing the same thing. He built something called the Messier catalog, which a lot of the astronomers use now. There are 110 objects in them, and he found these, and he catalogued this, and these are the fuzzy objects in the sky. Now, Messier did this for a different reason, and the story is also very interesting. Messier was doing this because the King of France at that time had announced prizes for people who can find comets. Comets were supposed to be the fashion in that time. And so people were sending in a lot of applications to get this prize. But it was found that most of these things were actually not comets. Comets move in the sky, whereas stars are stationary. And these stars, and if you look through a small telescope, you can see a fuzzy thing, that the nebulous objects that William Herschel catalogued. And these were essentially what people were thinking as comets. And so the king asked Messier, who was an astronomer at the Paris Observatory, to make a list of fuzzy stars which are not comets, right? And so that's the Messier list. So the Messier list and William Herschel's NGC catalog are the first and earliest sources still used of these fuzzy things in the sky. Now, people were aware from that time that not all stars are point-like and they don't twinkle. And I told you yesterday why stars twinkle. So here is a modern view of the NGC or Messier catalog. I picked 4 objects from the Messier catalog, M3, M1, etc. And I'm showing you how different they are. And these are pictures taken with modern telescopes. And we now know exactly the distance to each of them. And so we know how large they are. Because to them, these looked identical. They were all a few minutes of arc across on the sky. They were much bigger. They were not point-like. And so here it is. M1 is the Crab Nebula. It is 6 arc minutes across. We now know it is 2 kiloparsecs away. The Crab Nebula comes from the explosion of a star, something that happened in 1054 AD, we now know. And in 1054 AD, the star exploded. It was a supernova, and 1,000 years later, we are seeing it as an explosion. So it's a single star that is exploded, and that's why it's nebulous. Okay. M3, we now know, is a globular cluster. It has 10 to the power 6 stars, 1 million stars in it. And it is 16 arc minutes across on the sky. And it's actually quite much bigger than a single star because it's got 1 million stars in it. But because it's a 10 kiloparsecs away, then you see them roughly at the same size as the other things. Here is M27, which is a planetary nebula. That is what happens to a star when you come to the stellar evolution, as Professor Dipankar Bhattacharya is doing. You know that at the end, towards the end of its nuclear burning, a star goes through different phases in which they start losing mass. And here is a star that is finished nuclear burning in the center, and it's losing mass, and a lot of matter and it's formed a large envelope, which is called a planetary nebula. There's the most of the star is at the center, but it forms a very large nebula around it, right? And so this is still one star. So that's one star. That's one star. This is million stars. But they look identical on the sky. But many of these Messier objects or the NGC objects are like this M51, the Whirlpool Nebula, which I know now to be a galaxy. It's megaparsecs away, not kiloparsecs. It's megaparsecs away, but there was no way they could know that. We've measured the distance of that only recently. And it's the same size on the sky as the others, but it has 10 to the power 11 stars in it. 10 to the power 6 stars, 10 to the power 11 stars, 10 to the power 0, 10 to the power 0, right? So you can see that if you just look at fuzzy objects in the sky, you see very different things, okay? And this is why, till 1930s, we did not know the nature of these stars. We did not know that there are galaxies. In the 1930s, we started measuring the distances, and that was done by Hubble. Started measuring, and I'll take you through all the different ways in which you can measure distances to these things, accurately and not so accurately. And that told us that some of these things are 1,000 times or 1,000,000 times away than the other. And so if they are the same size on the sky, then they have to be much, much bigger. And you can find the actual light and actual mass by knowing the distances. Okay, so these are galaxies. We now know that the universe, the basic building block of the universe, are galaxies. And these galaxies are like molecules in matter, right? Those are the basic building blocks. But then galaxies have lots of stars in them and other things. There's dust, there's gas, there's I'll talk about all that, and gas, and then and dark matter, and stars, and all kinds of things. So, and about 20% of galaxies, maybe 15 to 20%, are nice and round. They're spheroidal. They're called elliptical galaxies because they are ellipses on the sky. But most of the galaxies in the universe, like our own galaxy, is flat, and they have, many of them have spiral structure in them, and they're fast rotating. Whereas galaxies like these, which are nice and spheroidal, they are very slowly rotating or not rotating at all. They are just moving, but not rotating. Whereas our galaxy is rotating very fast, and they are flat, right? High angular momentum. And then there are other galaxies which are not so regular. They're called irregular galaxy, and they're often small. They're called dwarf galaxies, and they have the other 5% or so. So this is what our own galaxy looks like. So our own galaxy is a spiral galaxy. And this galaxy, and you learn a lot more in later lectures on our own galaxy and about galaxies in general. But let's look at this in a very simple perspective. And I'm sorry if you know all this, but there are a lot of people here who have not been exposed to this. So let's look at this. So here it is. Here's a galaxy. A galaxy is very flat, like a chapati or a pizza, or it's just flat with a central bulge. Of course, this is not a real picture. You can't take a picture of our galaxy from being inside. But this is an artist's impression of what we know. And we know that we are a planet around a star. It's a very boring star, one of the smallest stars in the galaxy. Our galaxy has 10 to 11 stars, and the sun is one of them. Not a very big star. It's about 8 kiloparsecs from the center of the galaxy, right? And it's going round and round in orbit like that, 8 kiloparsecs, okay? 8,000 parsecs is about 25,000 light years, right? So we're not even at the center of the galaxy. We're far away from the center of the galaxy, okay? The whole galaxy is about 50 or 60 kiloparsecs across, in stars, that is. The stars that you see in the galaxy are that much across. And in the disk of the galaxy, there's a bulge in the middle. And right in the middle is, of course, the famous central supermassive black hole, for which, characterizing which the Nobel Prize was given this year. Now, the sun, we are going around the sun, we are looking at the universe through this little screen of stars that are around us. So think about where we are. We are in the disk of the galaxy, which is like this. And we are in a thin part of the disk. We are not in the thick part of the disk. So, for example, if our sun and Earth were here, then our sky would be completely full of stars. Yeah, you wouldn't be able to see any dark patch at all. Can you imagine that? Because you'll be looking through a much longer path length through the bulge of the galaxy. So we are towards the edge of the galaxy, which is good, because then we can see some stars, but not so much. Now, if you're looking out at the universe, you're looking through that little screen. And so all the stars that you saw in that picture I showed you here, all these stars belong to that little layer of stars, okay? But if you look in this direction, you will see a big, thick bunch of stars, and it'll go as a plane along the sky. And that's called the Milky Way. And that's why we call our galaxy the Milky Way. In Indian languages, it is called Akash Ganga. Akash Ganga, why is it? It's the river in the sky, because it's a river of stars. From India, we don't see it very well, because the Earth blocks it. You have to go to the southern hemisphere to see it very well. But actually, if you're in a dark place, on a dark night, a moonless night, you can see quite a lot of the Milky Way. You can see this part of the Milky Way and the upper part, right? So now, if you, for example, go to the southern hemisphere, this is a place I go to quite often. This is in northern Chile, in the Atacama Desert. On the Andes Mountains are some of the largest telescopes in the world, which I've worked with. This is a 4-meter telescope. in Tololo, and you can see the Milky Way. You saw that this is the plane of the galaxy, which is full of dust, and this dust is left over from when the stars were being formed. And some of the dust has come out of stars after their evolution. They add to the interstellar medium, and so that dust is there. So that dust actually blocks light at visual wavelengths. So you can see that dust. This is a real picture, by the way. That's not a real picture. This is a real picture. It's a real photograph. And actually, if you are in northern Chile, anywhere in the southern hemisphere, out there, away from cities, the Milky Way is bright enough that you can read on any night. You don't need the moon. You can read in starlight. Now, the other thing you see on the sky, naked eye, are two galaxies. We don't see them from India. These are two galaxies called the Magellanic Clouds. These are our, of the Milky Way, the two nearest satellite galaxies. The Milky Way has a lot of satellite galaxies, just like Saturn has moons. These are moon galaxies. So the Magellanic Clouds are large, and the small Magellanic Clouds are about 1,000 and 10,000 times smaller than our galaxy. And they are up in the sky all the time. And you can see, you just look, it's there, and they're like clouds, they don't go away. Right? So these are naked eye galaxies, and we don't have the privilege of seeing them from the northern hemisphere. Here is Sagittarius, where it's the center of our galaxy, which we don't see from India. And right in the middle is the black hole I was talking about, okay? But it's behind that dust cloud, right? Now, so remember that. So we are in this plane, and we're looking towards the middle of the galaxy. Then you see a Milky Way, stars and dust, they block the way. So actually you can't see galaxies outside in a picture taken that way. So you can see that it blocks galaxies outside. But if you look at the other direction, this direction, you can see stars, and you can see galaxies outside. And if you have a big telescope, then you can see through, and you can see galaxies in a distance. I hope that makes it clear. So this is a picture that became apparent to us only in the 1930s, 1940s, less than 100 years ago. People did not know anything about. Magellan discovered these things, in the 17th century, but 16th century. But he didn't know what these things were. Clouds and nebulae, they were not known. So here you are. I said that we can't take a picture of the Milky Way. Can we look at other galaxies to see what they are like? If they are like us, what they look like. So how would the Milky Way look like from outside? So here are some relatives of the Milky Way. This is another galaxy, which is very much like the Milky Way. It has 5 arms. And so this is what the Milky Way would look like if we go out and looked back at it. So you can see the sun would be somewhere there, right? Away from the middle bulge, going around in this. So this is a relative of the Milky Way. It's very similar to the Milky Way. Now you can look at it from, turn it around, look at it from an angle, and this is what it would look like. This is another galaxy that's at an angle, not face on like that, but at an angle. And here's a galaxy that would be exactly edge on, and you can see how it looks like our galaxy very much, because because we are inside the disk. So we look at our own galaxy, the rest of our galaxy edge on, and this looks so much like. If you take that part, it looks so much like the Milky Way that I showed you in the Chile picture. This one is taken also from another part of Chile, right? And that's the Milky Way. So this is kind of, you can see what our galaxy looks like. So here we are. So let's do something. I'm just telling you pictures, showing you pictures, telling you stories. Let's do something quantitative. So here we are. We are in. Some people asking me questions. Somebody has asked, sir, these space pictures which we see, are these real or made up by artists? So I think this person who has asked this question must be somebody who also thinks that we didn't go to the moon. And there are some people who think that we've taken pictures of astronauts landing in the moon or whatever. But I hope that's not what you think. I think if I interpret what you're saying as a sense of wonder, then it's wonderful. I told you that the picture that I showed you before, this one is essentially drawn by artists, but these are not. So here we are. So actually space is more beautiful than you think. Here we are. So here is our own galaxy, and it's got these spiral arms, as I showed you, and so these are all lined up by these molecular clouds where stars are being formed. And our galaxy right now, our sun right now, is passing the Orion arm. Now, what happens is that, and this somebody will talk about later on in the theory of spiral structure, the spiral arms are actually not, the spiral arms are actually over densities in the stars in the disk of the galaxy, and they are moving, the pattern that you see in the spiral arm is moving very slowly. But the actual stars in the galaxy are moving much faster. So the sun has gone around the galaxy many, many times in its lifetime, and we can calculate that. So let me do that calculation with you. How long does it take for the sun to go around the galaxy? Okay. So if we ask that question, let's see, the sun is now currently going around the galaxy, and we can measure we have measured this very accurately with respect to lots and lots of stars around us. We have measured the speed of the sun traveling in the galaxy, and it's at 220 kilometers per second. Do you feel it? I don't know. I don't feel it. The Earth is going around the sun at 30 kilometers per second, and the sun is going around in the galaxy at 220 kilometers per second. That is its velocity with respect to the galaxy rest frame, going around in an almost circular orbit. And the radius of that orbit is about 8 kiloparsecs. Actually, it has a motion in the direction perpendicular to the galactic plane as well, that it executes once in about 250,000 years. But that is a much longer time period. Okay, so it is going around like that. Okay, now, so it's very easy to then calculate how long it takes, because it's just a circular orbit. And you can do that yourself, but I normally, to do this kind of calculations, use a very simple set of units, and I'm going to teach you how to do that, because then I can do these calculations in my head. It's very easy, right? It's just a 2 pi r, which is your the length to go once, divided by the velocity, right? Will give you the time it takes to go around, except that I gave you the v, the velocity, which goes in the denominator, in kilometers per second, and I gave you the 2 pi r, the r, in kiloparsecs. Now that is difficult to do in your head. So what I do is I use the system of units which astronomers use, and I'm just teaching you this because if you haven't used this before, it's very easy. In every subject, there is a native system of units that people can use, so that you don't have to bring in a lot of conversions. And the quantity g comes a lot in astronomical calculations. And I like a set of units in which g can be set to 1. Okay, this particular calculation does not need g. It's 2 pi r over v, no g in there. But in many other things, you will need g. So I use the system of units. I put g equals 1. In my calculations to do with stars in a galaxy, I use the system of distance as 1 kiloparsec, and the unit of velocity is 1 kilometer per second. So they're very different, kiloparsec, kilometers. In any system of units, as you know from dimensional analysis, MLT are the 3 basic dimensions. You can choose 3 things that are independent, but the rest will depend on them, right? So here are the 3 things I've chosen. I've chosen g equals 1. I've chosen the unit of distance to be kiloparsec. You can see why. And because I've got the distance in kiloparsec. And I've got the velocity in kilometers per second, so I've chosen the unit of velocity to be kilometers per second. Once you have that, then it turns out, you can do this calculation yourself, once and for all, then you memorize the units and you use it. The unit of time becomes almost, it's 0.97 times 10 to the power 9 years. So that's a giga-year. So my unit of time is a giga-year. If I have my unit of distance to be a kiloparsec and my unit of velocity to be kilometer per second. So my unit of time is a giga-year. The only price I pay is that the unit of mass becomes a little difficult. You have to memorize that. And that is 2.3 times 10 to the power 5 times the mass of the sun. Not in kilograms. You can't measure things in kilograms in astronomy. So if I remember that thing, now in this particular calculation that I'm about to do, I don't need the mass, I don't need g, I just need 2 pi r divided by v. So 2 pi r divided by v, I can do this in my head now. 2 pi times r is 8, because my unit is kiloparsecs, so it's 8. My unit is kilometers per second, so the number I need is 220. So 2 pi 8 divided by 220, I can do that in my head. 2 pi is roughly 6, I don't know, 6.3 times 8 divided by 220. And if you do that, then you get a time, and your unit of time is a gigayear. So what you get is 0.2 gigayears, right? And so that is the time it takes for the sun to go around the galaxy. Now you know, and I know, that the sun and the earth are 4.5 billion years old. This people have measured from all kinds of things: radioactive dating, radiocarbon dating, all kinds of ways we can measure the age of the earth. There are all kinds of ways you can measure the age of the sun. And throughout in Professor Dipankar Bhattacharya's talks, you will know how from stellar evolution you can measure the age of the sun, age of a star. We know it's 4.5 times 10 to the power 9 years. So in its entire age of the earth has gone around the sun 20 times. So think about the journey it has had. It is now the Orion arm. It has gone around 20 times in its lifetime. And every time it has caused an arm, it has had something happen to it. It could have had tidal interactions. Some people think that in its journey, at 65 million years ago, when the dinosaurs died, we know that a lot of asteroids came and hit the Earth. That could have been because the Earth went through a particularly dense part of the galaxy. And from this kind of thing, you can figure out what might happen in the future as well to the Earth as the Earth goes around the galaxy. Might not happen in our lifetime, but 1,000 years from now or 100,000 years from now, we can predict by knowing where the Earth will be in the galaxy. Okay? So this is a very interesting and important calculation, but also shows you that that all these stars are going around at different speeds, and this is the typical speed of our sun. And we shouldn't think that we are stuck to one part of the galaxy the entire time during the lifetime of the solar system, right? So the final thing I will talk about is where we are in this whole system, and then I'll take questions. I can see a lot of hands up. Keep those up if there are questions to do with what we talked about today, right? Now, as I said, there are lots and lots of galaxies that are different kinds of galaxies, but one important thing is that even though I said that the basic building block of the universe is a galaxy, and there are lots of stars in the galaxies themselves interact with each other quite a lot, right? So, for example, the sun, which is in our galaxy, has been always part of our galaxy. It has not yet interacted in a major way with another big galaxy. But you can see the galaxies don't like to live alone. They live in small groups or very large clusters. There are very few galaxies who stay on their own. They are either have binary a pair, or there are little groups like this. For example, this is what is known as Stephan's quintet, 5 galaxies together, very famous little group of galaxies. And then they also interact with each other. And I'll come to that later on when I'll talk about what happens when galaxies interact with each other. And then galaxies crash into each other. Galaxies go very close to each other, pulling each other's stars out. And this is happening all over, always. So galaxies, because they are massive objects, they are extended objects, they have more of a probability of crashing into each other or interacting with each other. The collision cross-section or the interaction cross-section is very high. That is not true for stars. Stars are very compact things, very small things, and the typical distance between stars is much, much larger than the stars themselves. And that is why the probability that 2 stars will collide with each other is very small, right? So even as galaxies collide with each other, they can go through each other and the stars will not collide with each other, right? The galaxies, the gas will collide because that's the continuous medium. Okay. Now, just to take you through what our local neighborhood looks like. So As I said, galaxies like to live in small systems, and our galaxy lives in a little group. There are two big galaxies. One is the Milky Way, it's our galaxy, and the other one is called the Andromeda Galaxy, M31. And that's about 700 kiloparsecs away, about 0.7 megaparsecs away from us. And the interesting thing is that it's coming towards us. It's coming towards us at a speed of about 120 kilometers per second. And in about 4.5 billion years or so, it's going to collide with us and merge with our galaxy. And I'll show you later on a simulation of what we think it's going to look like. Now, each of these galaxies is surrounded by a lot of satellites, and I've shown here in this picture some of the satellites. For each galaxy, we know roughly about 40 or so satellite galaxies. These are small galaxies, much, much smaller than our galaxy, and they are going around our galaxy. I showed you two, remember, at the LMC and the SMC last time in the sky. Those are naked eye galaxies, and all the others are not really naked. And so Andromeda is full of them. In fact, we are discovering one satellite around Andromeda or our galaxy every year now. Raja Guhathakurta's group at the University of California, Santa Cruz, has been discovering. They've been discovering Andromeda satellites, probably 10 in the last 10, 15 years. So these are very tiny things, and you have to use big telescopes to find them. The average distance between galaxies, big galaxies, about a megaparsec. As I said, our nearest galaxy is about 0.7 megaparsecs away. And then, if you look at, this is a simulation, this is not a real picture, simulation of how matter is distributed in the universe, and you can see that it's very filamentary. I showed you at the beginning. So these blobs will be galaxies, right? And you can see the galaxies can be in small groups, and then there are big clusters. And the galaxies may form on this big web of matter in a small group, and then they move along these filaments to merge with the big cluster, to become part of the big cluster. And this we see, right? This is a simulation, but this is not, right? So here on the left is a slice through the distribution of galaxies near us. We are here, and each of the points in here is a galaxy, and we can now make three-dimensional maps, and I'll describe in the next two talks how we find distances to galaxies to make these three-dimensional maps. And from these three-dimensional maps, we can see that that's what the universe looks like. This was a simulation that showed you that it's kind of a web-like structure, but we can actually see that. We can see how galaxies are distributed in a web-like structure. And so this particular plot on the left has about 1 million galaxies in there, and these are just a slice through a three-dimensional slice through this a two-dimensional slice through a three-dimensional universe, right? So I'm going to stop there and see what questions people have. First, I'm looking at chat box, but I'll look at the participants box to see who has their hands up. So I can see Astha Chaturvedi, who has a question. Can you ask the question?
Yes, sir. Sir, I was asking that how do we decide on the radius of the celestial
The radius of what?
celestial sphere?
There is no radius of the celestial sphere. The celestial sphere is imaginary. You can take anything you want.
Is there any specific limit?
You just take 10,000 kilometers. I don't know what. You just imagine that. It exists only to show that if you have a plane, it intersects with the sphere in a circle. There is no celestial sphere. It's an imaginary thing. So for you, the celestial sphere can be 1 million kilometers. For somebody, it could be 100 kilometers, as long as it's outside the Earth.
Okay.
It's just an imaginary thing for visualization. It does not exist.
Yes.
Thanks. Anybody else? Now, Arjun Singh is next. Let me see if I can. No, I can't see mine. Arjun, can you ask your question?
Hello, good afternoon, sir.
Yes.
Sir, first of all, the lecture is fantabulous. Sir, I want to ask, sir, yesterday you taught about the star, blinking of stars, actually. So I'm curious that somehow can we means that you taught that it's our eyes which sense them blinking actually. So somehow can we see them not blinking with our naked eyes, without using any technique or without any telescope or camera, without anything?
Yes, of course. See, the blinking, as I said, is completely related to the fact that our eyes can only retain an image for 1/10 of a second, right? And then it initializes and it goes to the next image. This is why you can see movies. How can you see a moving picture on the screen? And that is because they are showing you 24 frames a second, and your eye does not remember something more than 1/10 of a second, and you see another one overlapping and you think it's all moving. Now think of any other creature which does not have that. For example, a mosquito, whose persistence of vision is much smaller than 1/10 of a second. They will see the movie differently, right? Now think of a camera which does not have that problem. A camera, you can actually keep it open for 1 hour. I do that all the time when I take an astronomical picture. That picture I showed you, taken by Dave Malin, of the whole night, the camera was open the whole night. Now, if you keep something open for a long time, it doesn't twinkle. But what happens is that the image gets bigger, broader, because the photons fall in a different place, and then it blurs the image. So you actually need, if you want to see things very close together and a high resolution image, what you need to do is to actually have an integration time that's very small. But then you pay the price that the image will move like that. So it's twinkle. Think about that. So, and that's one of the reasons why if you have an extended object like a nebula, then all that twinkling is happening inside that image. So you don't see the twinkling. You see a blurred image anyway, right? So
yes.
Actually, if you are a professional astronomer, if you do astronomy as a profession and you have to decode all this, you will have to disentangle all of that. So we do that. We try to take out, for example, the blurring effect of the atmosphere. We model it and subtract it. We have to do a Fourier analysis in which we essentially deconvolve an image with what we call the point spread function, which is to do with how a point's image is formed in a spread manner, right? All that has to be done. And so you might think it's very boring, but it's also very exciting. A lot of stuff has to be done in order to correct for the effect of the atmosphere or the effect of the instrument itself. The instrument, even if you go above the atmosphere, the instrument itself, the optics itself will have a blurring effect and stuff like that. So all that needs to be modeled. And so modeling the eye is far more difficult. So
yes.
we use instruments. Okay, thanks. Let me go to the next question by Himanshi. Yes, I'm unmuting you. Okay, please ask your question. Is Himanshi? Please go ahead.
It was nice hearing you about the galaxies. So my question is that you told about sun's orbit. Till now, we were just listening that sun is at rest, and today you taught us that the sun is moving around the galaxy. So what does that mean, that sun is at rest?
I never said sun is at rest. Of course, if you have to do any kind of calculation, or you have to have a frame of reference, right?
Yes, sir.
When you are calculating how you are moving, you take a frame of reference in which that tree is at rest, okay, and then you are moving with respect to that. So when you're doing a motion calculation, you'll have to find a frame of reference. So I was talking about a system in which we were thinking of the Earth is at rest, and then the sun was moving. Then you can imagine the sun is at rest, and then we are moving. And then you zoom out and look at what's happening, and the sun is moving along with us. But if you, in every calculation, take every single motion, then you won't be able to do a calculation, right? So everything is relative in the universe. In fact, there is only one frame that is at rest with the universe, and that is the cosmic microwave background. And somebody will talk about that. And that is because it came with the universe, and it's actually with the universe. And eventually, we measure all motions with respect to the cosmic microwave background, because that is the standard of rest. Otherwise, everything is relative, right? But then, in order to do any calculation of motion, you have to have a local frame of reference which you say is stationary, and then this is moving in that. And often it helps to think that the Earth is stationary, and then we can do our physics calculations according to Newton's laws as we do. But we think of the Earth as stationary. Think of how fast the Earth is moving. The Earth is spinning, is spinning at about 20 kilometers, 30 kilometers per second. It's spinning, right? And so if it's spinning that fast, then it's not at rest. Okay, so it's all relative, and then it depends on your calculation, what you're doing. Then you have to think of a frame of reference. I will look at some of the questions that are in the chat box. I have Arpita Saha asking, what is the utility of constellations nowadays? No, nothing really. I mean, it's we use constellations nowadays to again, as I said, mark places in the sky. So it's like saying, I'll wait for you at Ambedkar Chowk, yeah, or in Esplanade, or something like that. Similarly, I say, oh, I found a star, which is in the constellation of Leo, and things like that. For example, if you have a Leonid meteor shower and you want to see, you look at the sky and find Leo, and you know that the meteor shower will happen there. It's just that, nothing else. The utility of constellations is just an address, is to find an address in the sky. There are questions Shubham Pandey is asking, I told you about. Then there's somebody who's asked, Sukanya Das is asking, what is in the bright center of a spiral galaxy like our Milky Way? It's the stars. The bright center is just, there's a distribution of stars. The density of stars is much higher towards the center of our galaxy. And the bulge that you see is made up of stars. So actually our galaxy, and you'll hear this later on when people talk about the Milky Way, has the bulge of stars, which is kind of a spherical, it's like an elliptical galaxy. It's the central bulge, which is spheroidal, which is just full of stars. Then there's a thicker disk, and there's a thin disk. There are three components in our galaxy we now know. And so they have different scale lengths. But what you see with your eye in the picture that I showed you are essentially the stars. Now, underlying that, there is dark matter, there is galaxies, dust, there is the gas, which you don't see. The gas you see with radio telescopes, because it's neutral gas, atomic hydrogen, which emits a radio emission line, 21 centimeters. The dust, you can see it glows because it's at a temperature of about 50, 60 degrees Kelvin. It glows in the infrared. So you have to take an infrared telescope and map the dust, and you will see all that in this course. You will see how infrared astronomy is done. You will see how ultraviolet astronomy is done. You'll see how radio astronomy is done. And you can see different components of the galaxy in different parts of the spectrum. Okay, let me go to the next question in here, and that's Sachin Dubey. Go on and ask the question.
Yeah, so am I audible?
Yes.
Yeah, so it's related to the topic when you explain the season, right, when happens to winter on the Earth and summer. So, sir, it's actually related to the tilt of the Earth, right? How much at a degree our Earth is tilted, right? So my question is that if I move the Earth some more degree, then also the sun ray is going to fall on the every part of the Earth, right, after 24 hours. So how thousands years back the Ice Age made possible?
Oh, that is not related to that. The Ice Age, those were related to local phenomena, atmospheric phenomena, and those are to do with the ups and downs of the surroundings of the Earth rather than the sunlight itself. The last Ice Age was only 10,000 years ago, right? So in 10,000 years, this tilt does not change. This tilt does change, but it takes a much longer time. Okay, so the tilt 10,000 years ago, not 23.5 degrees, but 24.5 degrees, something like that. And so that doesn't make a huge change in the insolation, which is the energy received from the sun. Is that your question? Yeah.
Yes, sir. So,
I
my
think
second
are not
question
related to the sun's cycle or the sun's illumination.
Okay, so my second question is like when you were calculating the this velocity of the sun around the galaxy, so why have you taken the circular path like 2 pi? Why not the elliptical path like we most see the
It is not an
planets in a
elliptical
solar
path.
system?
It is very much a circular path, and we know this from the motion of measuring the motion of. See, and in a two-body orbit, the one body has an elliptical path around the other one, Kepler's laws. And that is because you're looking at a planet's motion around the sun. The natural orbit that comes out of it, if you apply Newton's laws to this system, is you get the Kepler orbit. And that is what you're thinking. When the Earth is moving around the galaxy, it's not a two-body orbit. The galaxy has distributed matter all through the galaxy. So as the sun is going around, it is not that it's pulled by the center of the galaxy like the sun pulls the planet. It is pulled by the entire mass that's within the orbit, okay, towards the center.
Okay, yeah.
So its natural orbit is not going to be elliptical at all. And we look at the distant stars, the stars around the sun, and and you can actually do very wonderful measurements outside the scope of a 1-month course to talk about how we measure the direction and motion of the Earth, of the sun. This was done in the 1980s. It's a very recent calculation, and you needed to actually measure distances to a lot of stars, etc. And I'll talk about that tomorrow, how we measure distances to nearby stars. And from that, people have done this calculation, and these calculations are getting better every day. And we know that actually the Earth's orbit in the galaxy very, very accurate, and it's very much a circle.
Okay. Yeah. So, so my one more question is that, so here, sir, recently we came to know that our sun is more closer than we earlier calculated towards the center of our galaxy, right? Recently we came to know. So, what we had made error earlier,
No.
and what we made correct.
Not appreciable. You know, when I was a student in a college, the distance that people quoted from the sun at the center of the galaxy was 10 kiloparsecs plus minus 3 or something like that. Then it became 8.5 kiloparsecs plus minus 1. Then it became 8 kiloparsecs plus minus 0.5, something like that. So there's always an error. And it's very difficult to measure very accurately the distance because you're using various methods. And now it has not changed much from 8, but it's all within those errors. The errors keep shrinking. And this is because you're measuring the distance of nearby stars and you're measuring the velocity with respect to them. I will talk about Gaia tomorrow, the satellite that is doing the largest survey of stars and building a three-dimensional picture. And I'll talk about how our knowledge about the three-dimensional distribution of stars and the velocities have gotten a lot better. So then you'll understand what has happened recently. What has happened recently is Gaia, the Gaia satellite, which was launched a few years ago, that is now doing these very accurate measurements of distances to stars. Yes. So quickly, let me go on to other people's questions. Ayush, go ahead. I have unmuted you.
Hello, am I audible, sir?
Yes, Ayush Garg, yes. Go ahead.
Sir, in the last summer, when there was lockdown, there was quite clear sky. There I saw a red patch of 0.2 to 0.3 mm. I am quite sure that is not the star that I have seen. And in the recent picture that you have shown me about the galaxies, it is seen that in the very center of it, there is a bright structure, bright bulbs of it. And as we all know that in the center of every galaxy, there is a black hole like this, which carries all the stars and surrounding matter in its orbit, like in a gravitational attraction force. So my question is, why there is so much brightness at the center in every picture of the galaxy, and there is not a black spot instead of it?
Well, if you look at the black hole in the middle of our galaxy, the angular size of that black hole, if you can calculate the Schwarzschild radius of the black hole, the black spot that you're talking about, you will find that its size in seconds of arc is 10 to the power minus 7 or 10 to the power minus 8 arc seconds. Right? So can you see something 10 to the power minus 7 seconds of arc when I told you that the atmosphere blurs things to 1 arc second? Even if you go outside the atmosphere, your instrument has a pixel size that is about 1/10 of an arc second. 10 to the minus 7 you'll never see. This is why when you look, you will never see. You saw the image of the black hole in M87 that was published by the Einstein, the Event Horizon Telescope. That was 10 to the power minus 5 arc seconds. And that telescopic image was made by radio telescopes all over the world, putting together, working in interferometry mode. So how can you look at the sky and see something that's 10 to the power minus 7 arc seconds? So you won't see the black hole. The black hole you can't be seen. What you can see is a concentration of stars towards the middle. The star distribution in the galaxy goes up in the middle. There has to be a black hole in the middle, but it's so small, there's no way you can see it. Otherwise, we would have discovered black holes a long time ago. And then, so what you see is the bright spot in the middle that you see is the concentration of stars in the middle, around in the bulge of and that's the scale. That's one of the reasons I'm going through this entire thing about the scale of the universe and looking at angles, etc., etc. If you are looking at astronomy, you have to think not in terms of millimeters and centimeters, but you have to think in terms of angles, in seconds of arc, minutes of arc, degrees, etc. Okay. And one of the reasons, very early on, I told you that the atmosphere blurs things. Particularly if you live in a city, if I look up at the sky, I would see my resolution of my eye would be a few seconds of arc. In Pune, it's probably 5 arc seconds. If I go outside in Delhi or Kolkata or Bombay, it will be 10 arc seconds, right? Because the atmosphere is so turbulent, it all gets smeared out. And so you see things that are very, very blurred. And if you're looking, you want to see a black patch with a black hole that is 10 to the power minus 7 arc seconds across. There's no way. Okay, next we have Sonal Dhingra. Sonal, I'm coming to the end. I'll maybe take a couple of more questions. Sonal, I've just unmuted you.
Hello, good afternoon,
Yes.
sir.
Go ahead.
So can you please explain more about the motion of Sun in a plane normal to the plane of Milky Way galaxy?
I didn't want to go into it. Look up the KZ law in books or on Google. KZ meaning it's the Z direction. Okay, so I told you that the Sun is moving in a circle or almost a circle in the plane of the galaxy, but the galaxy itself has a plane which is and then it's embedded in a halo of dark matter, which I'll talk about tomorrow. So and as a result, the motion is not completely a circle, but it's actually going like that. So it's like going like that in the Z direction, and also in the transverse direction. And this motion in the Z direction is caused by the distribution of matter in the galaxy, which is in the disk. So it has some kind of a cylindrical symmetry. And if you do a calculation of what happens to a point object that is moving in a cylindrical system, which is a disk system, you will see that it actually moves. It has a component which is a circular component and a component that has a Z component as well. In textbooks of dynamics, this is worked out as a Jeans equation that describes the motion in a cylindrical symmetry. So a disk has cylindrical symmetry, right? So in this particular introductory talk, I'm not going into these mathematical things at all, but if you start taking a course on galactic dynamics or stellar dynamics, one of the first things that you do is to learn about Jeans equations and motion in spherical symmetry, cylindrical symmetry. Till now, most people who have gone through Newtonian dynamics have learned about two-body dynamics, which are two-point objects going around each other, Kepler's laws. But it's fantastic to think about the motion of a point object in a distributed matter, right? And so then you start from, say, Poisson's equation in terms of distributed matter. Then you start looking at the symmetries, the spherical symmetry and cylindrical symmetry, and then you get wonderful orbits, the orbits that are possible. And they are very interesting orbits of point objects that go in cylindrical symmetry. One of them, I mean, the basic idea is that there will be a motion in the z direction cylinder, which means that perpendicular to the disk, and there will be motion in the plane of the disk. And they of course will work together, but they have two different origins. Okay. So you can look them up in textbooks. They are worked out. Thanks. Okay, Abhijit Talukdar, the last question. Abhijit, go ahead. You're not there. Okay, so I can't see you. I can see Sandesh Salunke.
Good afternoon, sir.
Go ahead.
Sir, just now you actually answered a part of my question, but still I'll ask it. Sir, as it's about the motion of the sun in the galaxy, I wanted to ask whether it goes with the plane of the orbits of the planets, or it goes above the. It's like, what is the head-on of the sun? It's like, does it goes and the planets go spirally around it, or it goes?
That is a very difficult question to ask. I don't think we know. I mean, you're talking of the relative orientation of the solar system's plane and the galaxy's plane.
Yes, sir.
Yeah, that I don't think we know yet. That's so because we can't really. It's all model dependent, and these are two such different scales that we cannot measure things so accurately. I think I'm absolutely sure we don't know it yet. Maybe in a 1,000 years we'll know that. Because the measurements that you need to make that kind of long-term calculations, it has to be done in simulations and stuff. We don't have data for that kind of accuracy yet. So it's a good question, but I don't think we know the answer. I don't know what the effect of such a thing would be on the plane of the solar system. That's also a very good question. Yeah, good question. We don't know.
Sir, can I ask a follow-up question?
Quick.
Yeah. So as you said that we can't see the black hole at the center, means it's very difficult to point out, and we just see a halo of light or stars. So how are we so sure about a black hole existing in our galaxy? As we have seen the black hole of some other galaxy, but how are we sure that there isn't?
They have to wait. I mean, either read about the Nobel Prize this year. I've got a whole lecture on it, but I can't give it. I think Ajit Kembavi is going to talk about that, right?
Okay.
So Kembavi's lecture on the middle. So you can. There are a couple of lectures on the black hole in the middle of our galaxy coming up.
Okay. Thank you, sir.
Right. Okay. Let me go through and see who else is there. Ishika Chand, are you there?
Yes, sir.
Yes, go ahead.
So my question was regarding the collision of galaxies. So do we know what actually happens when two galaxies collide?
Wait till tomorrow. Tomorrow morning, I'm going to talk about that. Yeah, all we know, of course, are through simulations and also looking at colliding galaxies around us. We can't wait long enough because galaxy collisions take 10 to the power 7-8 years, and much longer than a human lifetime. But our experience is to look at various different galaxies, various different systems, and to figure out how they are evolving. As I said, I gave the analogy of finding out how trees evolve by going to a forest. This is why we look at all different galaxies that are interacting. But we also can simulate these things. So we know that the gravitation is the only important force on large scales. So we construct galaxies, model galaxies, and have them collide. And they've been very successful in doing it. And I'll start tomorrow by talking about that. Okay. So I'm going to take a break now and come back tomorrow morning, and we'll do the third lecture, and I'll talk about interacting galaxies. At my usual time, 11:30. Today I had to displace my lecture. Okay, thank you very much. And I'm sure Dipanjan is setting up some form where you can put your questions, and then we'll try our best to answer them. But till tomorrow, bye for now. Thanks.